Welcome to this explainer. Whether you're literally designing complex chemical piping systems or just kind of nerding out over the physics of everyday life, mastering fluid dynamics is absolutely crucial. Today, we're going to cut straight through the noise and look at the exact fundamental rules that dictate how fluids actually move, from the oil running through a car engine to the water rushing through city pipes.
Now think about your standard kitchen faucet for a second. Crack it open just a tiny fraction, and the water flows out looking like a perfectly solid, glassy icicle, right? But crank that handle all the way open, and suddenly that exact same fluid coming from the exact same pipe instantly turns into this chaotic, rushing mess. So why the sudden shift in behavior? Well, this physical mystery is basically the perfect starting point for our journey today.
Okay, let's dive into this. When a fluid flows steadily, it essentially adopts one of two totally distinct personalities. First up, we've got laminar flow. That's our glassy water. In this state, the fluid travels in these perfectly parallel straight lines at low velocities. There is absolutely zero lateral mixing. But then you contrast that with turbulent flow at higher velocities. Here, order completely breaks down. It's replaced by these erratic cross currents and swirling circular eddies, which basically results in total chaotic mixing. To really grasp the mechanics behind what triggers this crazy switch, we have to rewind a bit, back to the 19th century. Enter physicist Osborne Reynolds. He wanted to take fluid dynamics out of the realm of abstract math and turn it into actual, observable science. So he came up with this brilliant classic experiment to visually prove the exact difference between these two opposing forces. Picture this. Reynolds sets up this large glass tank filled with water, keeping a constant water level, or head. Running right through the middle is a straight glass tube with a slightly flared entrance. Then, from a tiny tank up above, he injects a superfine, continuous thread of colored dye straight into the center of the water flowing through that tube. And guess what? At really slow speeds, that dye stayed as a perfectly straight, unbroken filament. No mixing whatsoever. It was literal, visual confirmation of laminar flow. But here's where it gets really interesting. As Reynolds used a valve to speed up the water, he hit this exact tipping point. We call it the critical velocity. This is the specific speed where that beautifully orderly flow just falls apart. As the water sped past this exact point, that perfectly straight thread of dye started to oscillate. It got all wavy, and then, boom, it completely disappeared as the water in the tube turned uniformly colored because of this sudden, chaotic mixing. Now, what's really fascinating about this discovery is how Reynolds formalized it into a universal rule. He realized that the flow pattern isn't just about speed. No, it actually depends on four distinct variables: the pipe's diameter, the fluid's average velocity, its density, and its viscosity. And he combined all of these into one incredibly powerful dimensionless group that we now call the Reynolds number. At its core, it just represents the ratio of the inertia force, the fluid's forward momentum, to the viscous force, which is the internal friction basically holding those fluid layers together. So, how do we actually apply this in the real world? Well, Reynolds gave us some incredibly reliable boundaries. If you calculate the Reynolds number for your specific system and it comes out to less than 2100, you can be certain the flow is definitively laminar. In this state, those viscous forces are totally in control. They're dampening out any chaotic movement and keeping the fluid layers sliding smoothly over one another. It's kind of like spreading a fresh deck of cards perfectly across a table. But if you push that calculation up to 4,000 or above, the game completely changes. The flow is always, without a doubt, turbulent. Those inertia forces have just totally overpowered the fluid's internal friction. High velocity takes the wheel, lateral mixing dominates everything, and the stream just fills up with these rapid, random eddies, violently crossing back and forth. Now, you might be wondering, what happens in between? Well, right there between 2100 and 4000 lies what we call the transition zone. And let me tell you, the flow in this region is highly unstable. It's constantly teetering right on the edge between laminar and turbulent. It might look perfectly streamlined 1 second, but honestly, even the slightest vibration in the pipe will cause those wavy oscillations to just shatter the flow into full-on turbulent mixing. So the crucial point is knowing how to distinguish laminar flow and turbulent flow like a professional. And to do that, I've got some simple, easy memorization tips for you based on their starting letters. For L, think laminar, lines, as in parallel lines, low velocity, and less than 2100. Super easy, right? And for T, think turbulent, tossing cross currents, and thousands over 4000. Anchor those associations in your brain, and you'll seriously never mix them up in the field.
All right, now that you've got the boundaries locked down, I want to drop a surprising mathematical truth on you, just to give you an extra professional edge. In a circular pipe that's experiencing that smooth laminar flow, the velocity actually isn't uniform across the whole pipe. The fluid physically rubbing against the pipe wall, it's practically at a standstill because of friction. Meanwhile, the fluid in the dead center is moving the fastest, which naturally forms this perfect geometric parabola. And because of that specific geometry, we know for a fact that the average velocity of the entire fluid is exactly 1/2 of its maximum central velocity. Pretty cool, right?
So we've covered the mechanics, but before we wrap up this explainer, I want to leave you with a real-world engineering challenge, just to test your intuition. Imagine you had a violently rushing, turbulent liquid in a pipe. How could you mathematically manipulate that pipe's diameter, or maybe even the fluid's viscosity, to force it back into a calm, smooth, laminar stream? Think about how those specific variables sit inside the Reynolds equation we just talked about. Keep observing the physics around you, keep crunching those numbers, and I'll catch